comfortable. And so the next presentation is, thankfully with a voiceover, Frank Gordon's own work on the LEC, and so it's a PDF with a voiceover, but I'll stay up here and I'll take any questions afterwards, and if I get in deep trouble I'll ask John Paul to answer as well.
I would like to start this presentation by thanking the organizers for allowing virtual presentations. Believe me, Harper and I would much have preferred to be attending the workshop in person so that we could engage in one-on-one discussions with our friends over some good wine that I'm sure Bill Collins has selected. While we can't do that, we do appreciate this opportunity and look forward to your questions and comments. The title of this presentation is the Lattice Energy Converter, LEC, Not Just a Battery. ICCF 24 was just 2 months ago. We made a presentation about the LEC, and John Paul Barbarian and Antonio De Stefano also made presentations reporting their replications. We also had a display table where participants could visit and conduct hand-on experiments and engage in discussions. One of the frequent comments was that the LEC is a battery. We actually considered calling our device a battery, but everyone knows how a battery works, and the LEC is at the very least a very unique battery. Also, the ability to ionize a gas without the use of radioactive materials or high voltages could have multiple applications not related to a battery. The battery that's actually closest to a LEC is a contact potential difference battery, but even there are several differences. The LEC does not require radioactive materials. A LEC may be comprised of low-cost materials rather than some of the rare earth materials that are required for conventional batteries. A LEC performs more like a current source than a voltage source. And we believe that these features that make the LEC unique also open a pathway to scale up the output without requiring hazardous radiation. In order to understand the conduction of electricity that we observe with the LEC, we have been studying the history of the conduction of electricity through the gas, which goes back more than 120 years. In 1895, Rontgen discovered Rontgen rays, which we now know as X-rays. 1 year later, Becquerel discovered radioactivity. That same year, J.J. Thomson and Rutherford published results on conduction of a current through a gas in the presence of Rontgen rays. In 1898, Lord Kelvin measured a voltage using radioactive uranium between two electrodes of different work functions. In 1899, Thomson published results stating that electrical conductivity in gases was due to the presence of charged ions. In 1903, Thomson published the conduction of electricity through gases in the presence of an electric field, but he dismissed diffusions of ions because he had a strong electric field. In 1903, Rieke published mathematical analysis on the approximately saturated currents between parallel plates. It included diffusion terms and provided a method for solution, but he did not make any analysis. That didn't come until 1932, when K.K. Darrow published a book titled Electrical Phenomena in Gases, where chapters 5 and 7 address the effect of ion drift and diffusion, and concludes that the voltage and current do not simultaneously decay to zero. What that means is the LEC is not ohmic. The speed of advance of these early research results was very impressive. Instrumentation was primitive by today's standards. A quadrant electrometer was used to measure voltage. The internet was still 80 years away. Publications were typeset by hand, and yet 7 of the items listed on this slide were made within 1 decade by some scientific giants. Since the LEC has many similarities to a contact potential difference battery, we studied the history of contact potential difference batteries, going back to 1898, when Lord Kelvin measured a voltage when using radioactive uranium between electrodes of different work functions. In 1924, J.B. Kramer gave a lecture at a meeting where he talked about a new electronic battery. His results were later published in the Electrician in 1924 and included the fact that Kramer had improved on Lord Kelvin's experiments by using radioactive monzonite sand and measuring both a voltage and a current. In 1951, Ohmart published an article titled "A Method of Producing an Electric Current," where he used 11 microcuries of radioactivity. He subsequently received a patent that included plots of voltage and resistance that are very similar to what we get with the LEC. In 2013, we first observed the surprising results that a palladium-hydrogen electrode would produce ionizing radiation without the need for naturally radioactive materials. We have conducted many experiments since that time to advance the understanding of the phenomena. In 2019, we learned that the palladium-hydrogen electrode would spontaneously produce ionizing radiation, even in the absence of an applied electrical potential. In 2020, we conducted experiments using iron hydride as a working electrode and also produced ionizing radiation and presented those results at ICCF 23 in 2021. During the time 2020 to 22, multiple people, including John Paul Barbarian, Andrew Erickson, Antonio DeStefano, Alan Smith, Alan Goldwater, and others independently replicated LEC results. Also in 2022, a U.S. patent titled Lattice Energy Conversion Device was issued to Gordon and Whitehouse on January 25, 2022. This slide provides a phenomenological description of a contact potential difference battery. When the electrodes with different work functions are electrically connected together, a very small current, maybe just a few electrons, will flow until the Fermi levels are equal. If the electrodes are placed in fluidic contact with an ionized gas, a potential difference or an ion concentration gradient will produce a voltage and current in the gas, completing the circuit with the external load. As long as the gas is ionized, the voltage and current will continue. Multiple parameters are involved in the production of the voltage and current, including the density of ions, the difference in positive and negative ion mobilities, the temperature of the gas, and the separation distance and surface area of the electrodes. K.K. Darrow explains this process in a book entitled Electrical Phenomena in Gases, chapters 5 and 7, which he published in 1932. This slide shows a possible phenomenological, physical, and electrical representation of the behavior of an experimental LEC contact potential difference device. For this representation, the working electrode WE is the ionization source, and as shown, it is not physically attached to either of the counter electrodes. The contact potential difference is due to the dissimilar work functions of the two counter electrodes, and is represented by the voltage source VCPD. The cell's capacitance is represented by C cell. The cell's internal impedance is represented by ZC, and the cell current I cell, which connect to the voltage source to the external load impedance ZL. Thus, I load should be equal to I cell. The voltage source, VCPD, is approximately equal to the difference in work function of the electrodes, but diminished by the output voltage, VLEC. The amount of current that a LEC can deliver to an external load impedance, ZL, is somewhat complicated combination of a number of density of ions, the electric field within the gas, the surface area of the electrodes, the effective separation distance between the electrodes, as well as the load impedance. By now, if I was there in person, people would probably be pointing out an error on the slide, since it implies that both plus and minus ions may go to each electrode. We all know that positive ions are assumed to be attracted to the low work function electrode, and negative ions will migrate to the high work function electrode. However, multiple parameters of LEC cell design are involved, leading to the situation where positive ions will actually migrate to the high work function electrode and negative ions migrate toward the low work function electrode. These results are predicted by theory and have been experimentally observed. This slide provides a brief explanation that explains why positive ions will diffuse to the positive electrode. Experimentally, we observe that as the load resistance is decreased from very high, which is essentially open circuit, to very low, which is approximately short circuit, the current and power both initially increase. However, at some point the power peaks and then it declines as the load resistance is further reduced, but the current essentially remains relatively constant. As the voltage decreases, the electric field also decreases and diffusion begins to dominate, whereby the number of positive ions diffused toward the higher work function electrode exceeds the number of negative ions. A similar process is involving the negative ions takes place at the low work function electrode, thus completing the circuit within the cell. This explanation is a top phenomenological description without a lot of detail. In reality, multiple ion drift and diffusion parameters are involved. In fact, even for the simplest contact potential difference devices, the equations describing the process is a fourth-order nonlinear differential equation which does not have an analytic solution, and the LEC is not one of the simplest contact potential difference devices. We are currently working on a technical note that goes into more detail describing these ion dynamics. The bottom line is that diffusion of positive ions to the higher work function potential electrode, as shown in the previous slide, is not an error. Some of the unique features of the LEC contact potential difference device includes things like, unlike conventional CPD batteries, the LEC ionizes gas between the electrodes without the use of naturally radioactive materials. Unlike conventional oxidation reduction batteries, the LEC CPD battery behaves more like a current source rather than a voltage source. In a LEC contact potential difference device, the electrolyte is ionized gas and no metallic ions, only electric charge, are exchanged at the battery's electrodes. Multiple materials, including low-cost, abundant materials, have demonstrated the ability to produce ionizing radiation. And the LEC has demonstrated the ability to be recharged with hydrogen after several years of continuous operation. We have conducted and tested several LEC designs, including a single working electrode device to produce ionizing radiation, a two-electrode device consisting of a working electrode and a counter-electrode, a device with a source of ionizing radiation with two or more counter-electrodes of different work functions, and a multi-working electrode device, for example, working electrodes comprised of particulates. This slide illustrates one of the cells that we designed to investigate the volta or contact potential difference effect. If the working electrode is emitting high energy particles, for example, alphas, we know that they will ionize gas, and based on the Bragg curves, 90% of those ions would be produced in the last 10% of their travel. For that reason, we designed this cell with an alternating set of fins of copper and zinc, and to position those fins near where the ions would be produced. It's also possible that if the working electrode produces gamma radiation, that could also impact the electrodes and produce a photoelectric effect. As you can see, the cell is basically designed and made from a mason jar that is about 3.5 inches in diameter. The working electrode is a 1/8 inch pipe nipple that is co-deposited with palladium and hydrogen. Alternating fin electrodes are approximately 2 centimeters by 8 centimeters and positioned radially around the working electrode. If the gas is ionized by energetic particles emitted from the working electrode, this design places the counter-electrodes in the region where the Bragg curve predicts the maximum ionization would occur. If the working electrode is emitting gamma radiation, this design places the counter electrodes where the gamma radiation could impact the counter electrode and produce a low photoelectric effect to ionize the gas. The cell is filled with hydrogen gas and at approximately ambient pressure and temperature. Also, as you can see in the circuit diagram below, we have the ability to apply an external potential between the working electrode and one of the fins, and we can also measure separately just the current and voltage between two of the dissimilar metal fins. This slide shows a plot of the voltage produced at various temperatures over time, as from the glass cell that was shown on the previous slide. You can see that as the temperature increased, the absolute value of the voltage between the copper to zinc fins and between the copper fin to the working electrode increased. Note also that there's a lag between the temperature measured by the thermocouple outside the cell and the change in voltage, which we attribute to the lag in the temperature change within the cell. We don't know if these results are produced by the Volta or contact potential difference effect or the photoelectric effect or the combination thereof. For the past several months, we have been focused on parallel plate electrode configurations because that cell design will allow increased electrode surface area to scale up the output. This experiment is similar to the experiment that Kramer conducted in 1924, where he used radioactive monzonite sand to produce and measure a voltage and current. We didn't have any monzonite sand, but we ordered some thorium dioxide powder that we plan to use after it arrives. In the meantime, we conducted a test using salt substitute, KCl, that is available at our local grocery store. For this test, we sprinkled KCl onto a copper electrode and placed a zinc electrode on top of the KCl. The plot at the right is the data from the load test conducted at room temperature. Due to the fact that KCl is known to be hygroscopic, we conducted a test in a kiln where we increased the temperature. As the temperature increased, the voltage declined and was approximately zero at 67 degrees C, and it remained approximately there as the temperature was increased above 100 degrees C. These results are consistent with the dehydration of KCl as the temperatures increased. We let the cell cool overnight, and by the next morning the voltage was back to the initial room temperature values, possibly indicating that the salt substitute had absorbed enough moisture to become an electrolyte. These results reinforce the need to conduct experiments to differentiate the difference between results from an oxidation reduction reactions and results produced by ionized gas. While waiting for the thorium dioxide to arrive, we decided to conduct another test using the same cell configuration as we had used on the potassium chloride test. For this test, we used palladium hydrogen particles that were produced during co-deposition and either didn't attach or were ejected from the electrode and settled to the bottom of the electrolyte. The particles were collected and placed on a flat copper sheet and allowed to dry, aided by blowing a heat gun onto the particles to make sure they are dry. Two thin strips of Teflon, approximately 1 millimeter thick, were positioned at each end of the copper sheet, and the zinc plate was placed on top. A load test was conducted at room temperature, and another load test was conducted when the cell, which had been placed in a barbecue, was heated to 180 degrees C. The data from both of those tests are plotted, and unlike the test with the potassium chloride, the cell voltage and current did not substantially change at the higher temperatures. The cell was taken to a lab and placed in a kiln to conduct a more controlled temperature test. Those results are still being analyzed, but while the cell voltage and function and temperature was not as high as the initial test in my barbecue, a substantial voltage continued to be produced at temperatures above 100 degrees C. Recognizing that these tests were conducted in air, we suspect that the small decrease in voltage at temperature could be related to more hydrogen diffusing out of the palladium particles than that which would diffuse in. Additional tests are planned to be conducted in a hydrogen gas environment. These test results are consistent with previous test results where radioactive materials were used to produce the ionizing radiation. For several reasons, the conduction of electricity in a LEC is significantly different than that of conventional use to describe conduction of electricity through gases. First and foremost is the fact that the source of the ionizing radiation is not naturally radioactive materials, but rather it is hydrogen host materials occluded with hydrogen. The LEC is a new source of ionizing radiation of an unknown type, and ionizing radiation can be configured to collect electrical energy. Phenomenologically, a spontaneously conducting LEC behaves as a current source and not a voltage source. The unique difference between a LEC contact potential difference and an atomic contact potential difference device are waiting to be exploited. Alan Smith and others, the team at Leonard Forum, have already proven to be a collaborative asset, and I encourage everyone to get into that web and keep track of the developments of the LEC as they are reported there, with hundreds of people involved. We invite universities, industries, individual researchers to collaborate with us in developing and exploiting the potential LEC device. The world needs abundant, low-cost, CO2-free source of green energy now, and if we are all involved, we can speed the process to get to that point. While the ability to produce ionizing radiation without the requirement for naturally radioactive materials is a significant discovery, several major challenges stand in the way of a useful green energy source. While palladium hydrogen and iron hydrogen have demonstrated the ability to produce ionizing radiation, we suspect that other materials and alloys could improve the current results and do so with lower cost materials and better metallurgy that can have a big impact. Once source and nature of the ionizing radiation is identified and understood, that knowledge can be applied toward improving LEC output. Additional challenges including extending the time that the working electrode will produce ionizing radiation and cell designs to more efficiently harvest the ions produced. Finally, a solution to the fourth order nonlinear differential equation will provide insight into the subtle dynamics of the ions within the cell. Thank you for your interest and your attention. We look forward to your questions and hope to be able to participate over a virtual connection. I'd like to also encourage you to follow updates on Leonard Forum, which can be found at the link shown below. Thank you.
Well, thank you, Frank. Unfortunately, he's not able to call in live, but if anybody has any questions, he asked me to proxy for him. So, you know, if you do. Yes, Bob.
Really interesting. Again, I hadn't seen this material before, so it's nice to be able to respond to it. So the 5 to 10 kilo electron volt particles that come out in exploding EVO can go on to produce more exotic vacuum objects that can cohere cosmic flux and it rinse repeat. So there's no reason why this wouldn't persist if you got the circumstances right. And also the ionization will produce photons, and if you have copper oxide in there, you'll get, as he correctly noted, the photoelectric effect, and that will feed the EVOs that are produced by the higher energy ionization radiation. And to that end, I would suggest using yttrium-coated copper instead of just copper oxide as something to improve the process. So that's my contribution based on what I've just seen.
Thank you. I've been looking into valve metals in general. I got a very good text written by a guy called De Breuer, working at Cambridge, and I think his research was mostly supported by companies like Osram and so on, who were into building radio valves. And
I mean, it's
a very useful source of information.
Yeah.
One of the things, by the way, you mentioned EVOs as being a potential charge carrier or a charge creation device, however you care to look at them. LECs are bidirectional. They conduct,
That's okay.
Yeah, okay. Yeah.
So, I mean, Ken Shoulders, he had an EVO generator, which effectively is created by an exploding charge cluster, which you're generating.
Yeah, sure.
And he passed that down a half-biased copper tube, and through the photoelectric effect of the EVO passing through and shedding some of its energy, you got more electrons emitted hitting the target, and you got a net gain in electricity.
Yeah, sure.
So what you've got here is a more passive system that is effectively, in my view, doing the same thing. And from my research to improve Ken's work, I found that yttrium-coated copper would probably be the best option out there for the photoelectric aspect of this.
Or can I say, post me your yttrium and I'll carry on.
It needs to be very thin.
Okay, sure. Are there any more questions?
Just simple question. The effect happen after hydrogen absorption or just from the beginning?
The effect is only after hydriding.
Sorry?
Only after hydrogenation, yeah.
Just after assembling?
With these very small surfaces. I can imagine that if you had very large electrode plates,
Yes.
you would see a voltage.
No,
just
because for a comparison, in our
course.
case, happened
Of course.
only after maybe 1 week of hydrogen absorption. At the beginning, 0.
Okay.
At least with my instrumentation.
We are the same thing.
But,
This only works after you electrolyze. It may work after.
okay, so you need some
It
conditioning.
It needs the occlusion of hydrogen within the metal, within the
Okay,
working
the same.
electrode.
The same, okay.
Well, you've all been stunned into silence. How splendid. We can... And yes, don't forget, Jean-Paul very kindly brought a working model, as it were. I had a lot of students like that, you know, model student, unfortunately, not a working model. And, but he's brought a LEC. If you want to come and look at it, then, you know, you can play with it, yeah.
Says that the ionizing... No, I don't need that, thanks.
For people online, is needed.
Okay, good. I think you're possibly right. Jean-Paul has got his own particular idea. Well, that basically, as the hydrogen diffuses off the surface, please correct me if I got this wrong, and the two monatomic hydrogens approach to form the molecule, they're squeezing photons out, not high energy photons, many, many lower energy photons. Thank you very much. I was always a good student. A very bad tutor, but a good student. You say we have online questions?
No, I didn't see that.
Okay, no online questions. Excellent. Yeah. Right. Yeah, now we wrap that one up. Thank you. The applause is for Frank, really. And I'll chair the next section. Are you going to do Alan Goldwater now?
Is there someone speaking in place of Alan Goldwater?
Well, I will look after the speaking if you've got his slides.
We have the slides.
Yeah, I work with him. So, yeah,
Okay,
he asked me to proxy if he couldn't. Yeah, if you couldn't do a phone-in, as it were. But
Who is going to...
Ubaldo, were you expecting to be next?
No, there is Alan Goldwater.
Yeah, Alan Goldwater here.
So because we are late of one presentation, we will move the last presenter of today, Carpinteri, tomorrow. Okay? Thank you, Carpinteri, for having accepted this.
speak to the slides. So I think quite a lot of you know Alan Goldwater, who lives in California and was at ICCF 24 recently. Alan's background is electronics, and particularly high fidelity electronics, but he is a very, very capable researcher, and he's certainly done his homework. He knows what he's doing. Let's begin. He did, by the way, ask me to proxy for him if he couldn't actually call in. So you got me again. There we are. So he talks here about the ICCF 23 paper that Frank and Harper presented, which I think was a bit of a surprise at the time, and possibly too much of a surprise, rather overlooked. And the thing he found really, this is new to me, I haven't seen this material before. So it's been replicated and discussed, as I say, and much replicated. And then after ICCF 23, Frank and Harper gave the very same electrode sample that they had at ICCF at Mountain View to Alan Goldwater to study, because he hadn't at that time had much success in attempting to replicate. I don't understand why, but I didn't. Frank and Harper visited his lab, and after that I think he saw the light, right? So this was a very small piece of stainless steel mesh plated with palladium, and they mounted it between some insulating PTFE with a little bit of the mesh, no bigger than a postage stamp, exposed in the middle. So, and Alan did a very careful study of its characteristics. There you are. He tells here about the way he constructed the anode, which is the counter electrode in this case. There, gosh, a very a very clear description of how he did it. Yes, and so just one anode plate with zinc chromate. When he says the two pieces were clipped together, I presume he means the counter electrode, the zinc chromate plated mild steel, and the working electrode, the little piece of palladium with its Teflon insulators. So then he did the like all electronics experts, he got out the oscilloscope, yeah, and there we are. And he actually knows how to use one. I know how to switch one on, but and hope I get it right. Oh, there we are. So there's the on the top there is the little working electrode, and the white bits you can see are the Teflon. I saw this at Mountain View, and there's the oscilloscope clips and the very hefty spring clips he's got there to make sure everything stays together and doesn't move. So there we are, and this is the 72-hour measurement across a 10 megohm load, right? So we had 600 millivolts. This is certainly a spectacularly good performing piece of palladium coated steel mesh, by the way. Mountain View, offload, it was producing over 800 millivolts. So he had around about 600 millivolts here. Notice how bursty, by the way, the radiation is. The same thing that Antonio Di Stefano has reported, measuring the clicks and so on. And you can see here voltage. While it's the trend is when there are excursions, they're generally down. There are more failures than less failures than successes, as it were. The general trend is to maintain a steady voltage. There are occasional downward bursts, and he's measured background radiation and the neutron count. Yeah, and none of that was significant. Nothing above background there. I think he's got a Ludlam a nice Ludlam pancake head Geiger, and I don't know about neutron equipment, but this is a man who knows what he's doing. So there, these are the X-ray spectra. Right. I don't know much about this data at all, I must confess. But I presume he collected this as, well, really it's background. Because as far as I know, he didn't detect any ionizing radiation from the LAC. But if anybody has comments on this slide, I will be pleased to hear them. Do you, Jean-Paul? You? Yeah, just background. That's what I thought. Okay. So he mentions here that there were a few significant peaks, but yeah. There you are. And of course, as he says, he's got 200 kilos of lead close by. And so there may have been the odd cosmic ray or whatever. So I don't think any of this shows that there is a significant source of radiation at all. There. Now there's one big peak there, 61.7 keV, and I think in discussion with Alan, he mentioned this to me, and he dismissed it as an oddity, another cosmic ray strike or whatever. This is very relevant to the discussion that we were having earlier, because here he measures at the bottom is the load in ohms, and on the left-hand axis is the voltage, and you can see also we have the current here. It's a plot of voltage against current, really, and with increasing load. And you can see that when you first put a load on the cell, the current rises, but you eventually reach a crossover point where the current falls away quite sharply. Yeah, this is not. This is one of a number of plots like this is produced. I've seen clearer ones, really. Yeah, but there you are. So, and also he's measuring there the power, total power. And as you see, it climbs to a certain point, and then as you reduce the load, yeah, and you approach your short circuit condition, the power drops off again. This is a very interesting photo, I think. It's there is something here. I did discuss a butchered version of this with Jean-Paul earlier. He used a Bruker EDX, and basically it was he persuaded his electron microscope to work in another way, as it were, as a radiation detector. And I think, as well as looking at the microstructure, so there's the co-deposited coating, as you can see on the mesh, and under higher magnification, it looks like popcorn. Yeah, basically, the general effect is popcorn, and it has a huge surface area, so this is very good from the point of view of hydrogen absorption, and if you were Ed Storms, you'd be very interested in the fact that this popcorn surface contains many cavities and cracks and micro cavities and so on. So it does have the potential to actually house many nuclear active zones, or NAEs as Ed calls them. But once again, there was no radiation here, so that's purely speculative. A very interesting collection of elements shown in his SEM work there, and he isn't sure about the source of many of these materials, and neither am I. We had I did wonder whether Frank had used some contaminated electrolyte when he made it, or whether, I know he's used a lot of galvanized materials, for example. And if he used some hydrochloric acid that had been in contact with the zinc in some of his old stuff, that would explain the presence of the zinc. though I have a suspicion that zinc is somehow catalytic in this process, or certainly it's a good dopant. Zinc is a good dopant. So good spread of, and rather puzzling spread of elements there, which I don't think anybody's explained satisfactorily. And do you have any thoughts about that, Jean-Paul? Yeah. That's a very good point, Peter. Thank you very much. Yeah. And the sodium? Oh, no, no. Yeah, yeah, sure. I think so. I think so. Yeah, so we're not, nobody's claiming transmutation here. Absolutely. Yes. Yes, it's even in your socks. I did a job for Nike last year because they produced a new sports shoe and the insoles kept falling out, and basically it was the sodium in your sweat that was destroying the glue. They tried a new glue, it didn't work. Okay, this is an area with the zinc. There we are. There is some sodium there too. Yeah, but there are both elements on the sample. He felt the distribution is different, and 11% zinc. It's quite a lot, really. So I think this is contamination, but I don't know for sure. Mm-hmm. Contamination. I think that Frank had actually used some electrolyte, some hydrochloric acid electrolyte probably, that he'd used before. Yeah, because he often recycles stuff, as we all do. Yeah, and it may be, or maybe he used a zinc electrode for some part of this process. I don't know. So this is how he looked for the radiation, as you see, right down to 150 EV. Yeah, and there you are. And this was done in Spectra, in a vacuum, so there was nothing. There was no ionization of the gas. There was no gas, but then again, he didn't detect anything that might cause ionization. So. So he saw he says here, he saw the zinc line, but this is the EDX, of course. Yeah, yeah. So, but he confirmed it. So there you are, 220 nanowatts. Yeah, so we've got a long way to go before it even lights an LED. Per centimetre squared, and of course, even if you have a square metre, you've not got of electrode, you've not got terribly far. As he says here, I've never seen it produce a volt, but I've certainly seen it produce over 800 millivolts. But it depends on the temperature. Maybe his lab was warmer than Mountain View. Surface morphology, popcorn again, and many different sized particles. And there you are. He mentions once again the zinc and the sodium, and the fact that there is no significant X-ray emission. There we are. Is that the end? Thank you for your attention. Yeah. Thank you, Alan. The cheers for him. I'm merely the monkey that carries the hat.
That rather goes along with Jean-Paul's idea of it being X-rays, because basically what you've shown is that when there was a vacuum there, okay, you see no radiation at all.
That's right.
Yeah. And we know that when air is there, when gas is there, then it arises. So that rather points to Jean-Paul's explanation that the likely source of ionization is X-rays.
I agree. Something like that. It's something very close. Either that, or we could invent a new particle. This is a terribly popular thing. It's terribly popular, you know. They're very... Yes, Bob.
I have used that Toshiba in his lab.
Yes.
It's in a double roofed, it's got a roof and another roof above it, and it's got multiple walls and thick walls internally.
Yeah.
And then the device is then placed into that Toshiba, which has a steel casing, which I suspect necessarily is grounded. This combination will prevent the exotic vacuum objects from cohering the cosmic flux of relic neutrinos, and therefore it will shut down their activity. And so I would not expect to see any X-rays inside that cavity or vastly reduced activity. And depending on how much time it was in there before it was run, then you wouldn't see it.
That's an explanation for which I thank you. Yeah.
Okay.
Yeah. Are there any more questions? Amazing. Everybody's satisfied. Well, oh, Bob, yeah.
I have a limited amount of monazite that I took in speculation in 2013 from where I was living in Kerala.
Yes.
It's extremely active.
Yeah.
It will make your Geiger counter go absolutely skits. I know where I can get it from, but I need to go to India again. But if there are some serious parties, I will send some to Alan, because I was not aware of that 1920 whatever paper that was referred to by Frank, that J.B. Kramer 1924 paper. But it is very interesting.
I think Frank in particular will be very seriously interested.
Okay.
And will be the obvious man to send
Okay,
it
so I'll send some to
because he's
him.
been looking, yes.
Yeah, you can't get it easily, but I know
No,
exactly
no.
where you can get buckets full.
Yeah,
And it
okay.
is incredibly active.
Yes, sure.
Yeah.
Yeah. It's off the black sand beaches.
So it's in placer deposits in Kerala, and it's from the monazite. They have like the largest thorium deposit pretty much on Earth, and I used to live in it for 8.5 years. It is on the beach. It's on the beach.
Yeah, it's the black sand beach.
It's all the way down the coast of Kerala.
Yeah.
And they make a lot of titanium there, and also when I look at it, it's got a lot of so-called rare earth, but they're only rare because people don't mine a lot.
That's what they're called. Yes.
Yeah.
That's why they're rare.
But there is a huge amount of thorium in there, like the grains. So it produces, you put my Geiger Muller counter on it and you literally, no, not Geiger Muller, well, you do that as well.
Step smartly back.
If you put your spectrometer on it or your Geiger Muller, you literally want to leg it out of the room because it squeals at you.
Well, thank you very much, everybody. I think we're going to have, who go next? Yeah? At least you've got some serious science to look at now. Thank you. You've been very patient.
Don't worry.
That's okay.
Schermo intero.
Okay, we are.
Okay. It's my turn. You are tired, so no question at the end. Okay, the title of the presentation, experimental, I didn't touch. Okay. Then the title of the presentation is Excess Heat from Nickel and Copper-Based Powder Samples with the addition of suitable low work function materials and dispersant, heated up to 700 degrees centigrade in a hydrogen atmosphere. I received this material from the lab of Francesco Celani and collaborators. This is the outline of the presentation: experimental setup, data set, Reference tests and calibration, hydrogen test examples, extra heat evidences, final consideration. This is an overview of the reactor. The reactor has the name R20 because it was designed to replicate the Mizuno experiments. And I used to, for attempt to replicate the Mizuno experiments. So you can see that the reactor is quite big. The dimension is, the volume of the reactor is about 3 liters. And you can see the closing flange where there is positioned the heater, and very close to the heater there is the stainless steel tube containing the material to test. This is the sketch for the inner part of the reactor. The heater is separated by the flange by a ceramic insulator to avoid to transfer heat to that direction. That remains quite cool during the experiments. Here we have a very simple power supply. Is a variac. The computation of the power in is done with an Arduino setup connected to a computer that indicates the power directly delivered to the heater. And there is a USB connection from Arduino to the computer. And here there is an overview of the complete setup. You can see that the reactor is suspended in a frame to avoid to decrease the insulation towards the ambient. And we have the system to measure the three main temperature: the ambient temperature, the inner temperature, and the temperature of the reactor taken in the center of the reactor by a K thermocouple. There is also a mass spectrometer to measure the purity of the gases and eventually the change in composition of the gases after experiments. There is also the system to deliver hydrogen. There is a hydrogen generator that is controlled by the RGA to be sure that hydrogen is pure enough inside the reactor. Okay, we have also to be sure that the external thermocouple measures with good stability the temperature. There is also a supplementary measurements done with a small spot pyrometer, just to be sure that there is no instability for all the experiments, that the thermocouple should go okay. This is the data set. The main parameters are the three temperature: internal, the temperature of the chamber, ambient temperature, the pressure, and obviously the power in. And other parameters are useful to make the calibration, the comparison between the thermal results. Here we have a reference done with another kind of material inside the reactor with the same configuration, because it is important to compare the results with the hydrogen towards the calibration to have the possibility to compare the thermal behavior of the reactor internally and externally. So this overposition, the overlap of four different experiments done with the same configuration with a material that did not give any extra heat. To do the comparison, we can have two choices. One is to overlap the curves, because with different gas and different pressures, you cannot have exactly the overlap of the thermal measurements. So we need to use a multiplicating factor to overlap the curves, or we need to make the derivative of the curve just to see if we have an inflection during the experiments. The inflection of the curve means that you may have some extra heat production. But to have the derivative of the curves, you need to make much more points of measurements. So I prefer to make the fitting overlapping the curves with a multiplicative parameter. This is the calibration done at the beginning of the experiments and at the end of the experiments. We have three different calibrations. These curves are for internal temperature. We take this parameter subtracting every time the ambient temperature, just to have to eliminate the influence of ambient temperature changes. And you can see that the internal temperature for calibration, all the curves up to 700 degrees, they overlap quite well. The same is not true for the external temperature of the reactor, because there is a small shift between the first calibration and the final calibration in helium, because there is a small change in the color of the external of the reactor. To have a reference for the results in the experiments, we can overlap also the three calibrations using exactly the same approach of a multiplicative factor, very simple mathematical operation. What was impressing, first of all, was the behavior of the pressure inside the chamber. Here we have the first calibration, the blue line, and the first three tests in hydrogen. Before to make tests with hydrogen, the material was activated with 10 cycles at 400 degrees for 1 hour. And the first experiment in hydrogen at up to 700 degrees is the yellow curve. You can, this is the normalized pressure, just to compare the pressure that not always is exactly the same at the beginning of the experiment. We operated at about 260 millibar, quite low pressure. You can see here that at a certain power, about 100 to 150 watts, we have the yellow curve that goes down respect to the reference. It means that hydrogen was absorbed by the material in a quite strong way, because when we stopped the experiments and becoming into the environment temperature, the pressure from 260 millibar decreased to 60 millibar. Being the volume about 3 liters, the quantity of the amount of hydrogen absorbed was quite high. And considering that the weight of the powder was 7 grams. The second test is the green line, and you can see because this big absorption during the first test, it was necessary to refill the reactor because I wanted to make other experiments at the same pressure of the previous one. So the hydrogen was changed and refilled up to 260 millibar. And the second test, the green line, that is visible only in the at high temperature, the pressure was increasing since the beginning of the experiment. It means that the hydrogen absorbed was desorbed into the reactor. And at a certain point, you can see that the increase of the pressures is much less. And at the end of the experiment, the pressure and the environment temperature was higher than the beginning. So I made the third test with the same, without changing hydrogen, to try to make absorption of hydrogen in the range of temperature from 500 degrees to 700. And you can see the red curve, that the operation to go directly to those temperatures was a success, having a reabsorption of the hydrogen. And this test was one of the best showing a quite high extra heat. And this is exactly the behavior of the temperature during this third test, where I forced a reabsorption of hydrogen from 500 degrees to 700. You can see here two couple of graphs showing raw data comparison between the experiment and the calibration, and the same curves after the overlapping operation. You can see that at a certain point we have an inflection of the curve in hydrogen, and meaning that there was the initiation of extra heat production. The same effect was detected from the temperature of the reactor. Here in this slide we can see the comparison between calibration, the first test, yellow, the second test, and the third test. Consider that the third and the second test have a common part from ambient temperature to 500 degrees. And all these tests gave this inflection of the curves that are a signal of excess heat production. This is the same experiments considering the temperature of the reactor respect to environment temperature. You can see that the effect of extra heat for the temperature of the reactor begins a little bit later respect to the internal temperature. And this is due to the fact that the reactor is quite big and we have dispersion of the heat produced by the material in the center of the reactor, and we have dispersion of energy to the edge of the reactor. I have elaborated a thermal model of the reactor, and this effect is completely explained. Here we can see the third test, just having together the behavior of the internal temperature, the behavior of chamber temperature, and the behavior of the pressure. You can see that the extra heat production begins when the pressure began to be reduced because absorption by the material. This is the point. Okay. Here we have another, in total I performed 14 valid tests, and after the third test we have a decline of the extra heat production, so we have several tests where the extra heat is much less than the third test. Making a treatment to the powder, making an oxidation to regenerate the behavior of the powder, we had, with the next test, we had these very good results again, having a quite high response in terms of extra heat. Here we have together again the internal temperature behavior, the temperature of the chamber, internal temperature, chamber temperature, in comparison with the calibration with a small extrapolation because the calibration was not at a so high temperature. And here there is again a quite good behavior about absorption of hydrogen. So we can say that the absorption of hydrogen plays a good role in terms of extra heat, possibility of produce extra heat from the material. There is a note about the test 9 because the test 9 was done after the oxidation of the material. Then we changed the hydrogen, removing the air for the oxidation. And during the test, there was absorption, but there was also consumption of hydrogen due to the reduction of the reaction with oxygen remained into the powder. But if you can see here, the calculation of the hydrogen consumed by the reduction of the pressure takes into account of a small energy respect to what is produced by the extra heat. I told before that we can have two methods to compare the curves, and one is the overlapping of the curves with, from the experiments and the calibration, or measure the thermal resistance of the reactor. And here there is an example of the behavior of the test 9 in respect with the possibility to make the derivative of the curve of the temperature of the reactor. Oh, sorry. This is the thermal resistance calculated with a derivative of this curve here. You can see clearly here that the slope of the curve goes in the good direction for us. It means extra heat, and it is confirmed by the behavior of the thermal resistance that if there is no extra heat, should go down continuously. While if you have a stability of thermal resistance or increase, it means that inside the reactor something happens in terms of extra energy. Here there is an evaluation of the extra power produced in a conservative way. We compared the calibration temperature and the experiment temperature with hydrogen. And you can see that this distance is the power, means the power. It is about 80 watts. If you could measure this difference from here to the extrapolation of the calibration, it should be much more. For the same test, I said that the temperature of the reactor doesn't follow in terms of extra heat and extra power, the same value we have outside the reactor, because there is dispersion inside the volume of the reactor to the edge of the reactor itself. So here we can estimate about 60 watts from the temperature of the reactor. And here have the curves of the test subsequent the test 9. You can see that the powder has been in some way changed, and the extra heat is much less, and also the behavior of the pressure, you can see here, is not quite good. It doesn't decrease too much. So where inside the reactor there is no absorption or strong desorption, the extra heat is not so big. In conclusion, in total, I performed 14 hydrogen tests from April to June 2022. For all tests, the comparison with the helium calibration showed more or less clearly the activation of thermal anomalies in the material, such as excess heat. Taking into account that the duration of this test is typically 6 hours, in the most significant tests, the production of excess heat was prolonged for over 3 hours. It means that in the middle of the test, we began to have extra heat. The mechanism underlying the thermal anomaly remains misunderstood, even considering that the monitoring of neutrons and gamma, always active during the experiments, did not show any deviation from the background. The results of this series of experiments are to be considered extremely encouraging in view of application for the generation of thermal energy at low cost and low environment impact. I thanks too much Francesco, Cesare, and Pietro for making the powders available and for the guidance to suggestion during all phases of the experimentation. Thank you for the attention. There were questions.
Thank you very much for this very interesting presentation indeed, Baldo. Is this powder the same one as the one that was tested in Uppsala?
No.
No, it was a different one.
By Francesco.
It was the same batch, the same, but the arrangement of the reactor and the excitation was very different. The same powders, just because different excitation. Okay, same powder.
What was the mass of powder you were using? How many grams?
How many watts?
Grams, weight.
7 grams.
7 grams only.
I use 7 grams.
Can you put 70 grams?
Yes, I did. I do.
You can?
I can.
Sure.
Yes.
Then you have self-sustaining system.
I need to have a cylinder of stainless steel big enough to to be connected to the heater.
You said a very important thing. You made the calibration also with a powder, an inert one, but there was a powder in this reactor.
Yes. During calibration, there was always the powder.
Also 7 grams?
7 grams.
As well. Okay.
It's still inside the reactor in this moment. I started with the calibration. When I put the powder inside the reactor, I started the helium calibration. After helium calibration, I made the activation cycles. The activation cycle, 10 cycles, measuring the purity of hydrogen every cycle, changing the hydrogen every activation cycle, 1 hour, 400 degrees. And was amazing to me is the absorption with the first test in hydrogen. Very strong absorption. If you can calculate the ratio between the 7 grams of power, considering all the copper or nickel, all nickel, and the moles of hydrogen absorbed, the ratio between hydrogen and the metal was about 0.5.
Sorry, you mentioned the fact that a mass spectrometer is included in the setup.
Yes.
But perhaps I skip the point. Did you detect something during this measurement?
I measured after the test with oxidation some small amount of water inside the residual gas. Anytime I fill the reactor, and anytime I remove the gas from the reactor, I check with the mass spectrometer the composition. The only variation are in the quantity, the small quantity of water that may change, especially when you have hydrogen after the oxidation for regenerating the powder itself.
If I understand, you tried only once this oxidation and reduction?
No, I tried almost 2 times. First time I had no so good results as the test number 9. Before the test number 9, I tried to reactivate the powder with an oxidation, but was not prolonged enough, in my opinion. So before the test 9, I prolonged oxidation for more time.
Ubaldo, how did you introduce the oxygen when you make the oxidation? Because it's closed cell, so you need to feel again the oxygen, the air in the system.
No, it is possible to open the vacuum circuits.
Yes, but immediately all the oxygen is sucked by
I put
the nickel.
the air.
You have to pump out and then put air again. Just air.
I opened the reactor.
Yeah, I understand, but there's no flux of air.
No flux. I opened the vacuum connections.
Yes.
I make air going inside the reactor.
Yes.
Because I cannot measure pressures over 1000 millibar, yes. I reduce a little bit the pressure of the air, making a vacuum with a mechanical pump, and I perform the oxidation, closing the valve of the reactor.
Okay.
Very simple operation.
Thank you.
But if you oxidize the material, absorb the oxygen, and you have...
Yes.
If there is no flush, as Arnaud says, there is air coming in?
No. I have steady state air inside the reactor, and then I put out the air, but before I check with the mass spectrometer how the air has been changed.
So
the composition of the air is changed after oxidation. I measure the quantity of the reduction of oxygen in the air. Comparing.
Excellent. Then how much oxygen was introduced in this sample?
Consumed.
How much oxygen was consumed
exactly.
Because of the oxidation? You have 7 grams of powder.
Yes.
You consume how much oxygen?
Yes.
How much?
I have the spectrum. I don't remember exactly now. I have the quantities.
It was fully oxidized or just a little bit?
I don't know the material, how much. I measured the difference between the oxygen in the air before and after. I can say the difference in partial pressure of oxygen. Maybe we did the calculations, I don't remember. We did the calculation of oxygen consumed. But what is important is the oxygen consumed with the test after the oxidation that reduced the pressure of hydrogen.
Okay, just feeling some after oxidation, we keep to room temperature and check the pressure drop. Later we give Ubaldo give again hydrogen and check what happened, especially about energy balance. So if we consider only the usual chemical reaction, hydrogen-oxygen, the gain, we can say, integrated over time, is about 267 times the chemical origin. The gain. Okay. So it seems no mistakes, anyway. So chemical balance, cold fusion balance.
At this point, we should remember a paper by Grozek. I don't know if all of you are aware of that. This is an experiment. We made alternative oxidation and reduction, and each time there was reduction, if I remember, there was excess heat. It means that he was saying more heat than just the chemical reaction. All of you should know about this. Do you know this paper, Bob?
I would like to.
This time, the balance was over 200 times the chemical. So it's age amount. So just this was the difference. Not little increasing, you have a double. So exactly is 257, if mathematics was correct.
Okay, thank you, Albaldo, for the presentation. I have one question. Stainless steel, is that the make of the DOR or whatever it is you have?
The
reaction chamber.
The reactor chamber is stainless steel, yes.
Okay, so...
3 liters volume, a little bit more.
Okay, so on the assumption it's producing what I think it's producing, might I suggest you have an iron, soft iron reflector around it? I know that's going to change the way you measure it. Or some borax in a concentric tube or make or sheets. Because in the Russian research, they are saying that you're losing this strange radiation from a metal that's not magnetic.
Mm-hmm.
And so you're losing a lot of the potential energy gain. So in Parkhomov, he always uses like an old ceramic-coated iron dish to reflect the strange radiation back.
Okay.
So
now, I didn't change the configuration of the reactor after the Mizuno attempts to make those tests. So the internal of the chamber is an ache, and there is nothing to screen the radiation.
Okay, so well, you're not going to detect it in normal ways. So the amount is how many grams?
7.
Okay, so Alexander Parkhomov used 1.6, so that's significantly more, and he used that in his 225-day reactor. In other Soviet, Russian work, they have used a lot more than that amount, like in the kilo amount. And they observed a flux of strange radiation that scared them, frankly. And it's when you reload the hydrogen, that's at the maximum risk point. And we observed something with Chelani wires in 2013, which is the same phenomena, in my opinion. There is a detector that you can build, and it's based on a nickel plate and neodymium magnets. And you have it at a certain distance from the reactor on a string. And when you load the hydrogen, of course this is with a lot more of the nickel or whatever it is you've got in there, you should end up with the detector spinning. But you might not see it. You should have they had a ceramic tube, and you might get it through the stainless steel.
I cannot see what happens inside the reactor either.
No, but this is outside of the reactor. It's a physically large thing that you can arrange if you have enough material. So if you do whatever was asked for you by Paul, you might be able to, like, he had it 22 centimeters away. The spin field is quite intense, and then it's basically zero. So you need to have it so that the fulcrum is at the point that you get the spin field. In theory, but there's other ways to detect it, which you could use as well, but I don't know whether the flux is high enough. You have iron 57 foil with a normal magnet north or south on the back, and then you look at the fine constant of the flux that's coming out that gets captured in the iron 57 nuclei. But I've shared all this, but I can share the specifics with you.
Okay, thank you. But
well, they say they stopped working on it until they understood how to shield for this radiation because of Bajatov's death. So what I'm saying is when you reload those reactors, until you know what's happening, until we all know what's happening, do not be in the location of the reactor for around about 3 minutes.
okay, but I don't want it to change the configuration of the reactor because otherwise I lose all the comparison with the tests done before.
But the two methods that I've said that potentially could give you detection of what's coming out at the time of reloading do not change your configuration. The first points were to increase the excess heat, which you might consider further down the line.
Okay.
Okay.
Thank you.
I want to know, you say about mass spectrometer. I want to know what kind of mass spectrometer did you use in your experiments?
The name of
yes,
the supplier
and
of
characteristic and reliability and sensitive.
The name is X.
And chromatomass spectrometer and also...
The spectrometer is able to measure from 1 to 100 mass units. And the supplier is...
unit and ppm, ppb, and sensitive.
You measure the partial pressure inside the chamber of the RGA. Usually the turbo pump is able to reduce the pressure inside the chamber of the spectrometer down to 110 to -8 torr.
Okay.
And you have a leak valve, a special leak valve to supply the gas you want to examine.
Okay.
It's not easy.
This spectrometer measurement only elemental
the
and
apparatus
isotopic.
is quite simple. The cost is not huge, about 9,000 euros.
I know. But we know that all analytical devices have its disadvantage. Now, what I want to ask, and what do you eliminate this disadvantage? But we know what all analytical device has its disadvantage. Because I work with mass spectrometer with inductively coupled plasma, this device is its disadvantage, matrix and spectral and non-spectral matrix effects, which influence that result analysis. I want to know how did you eliminate this disadvantage?
Eliminate what?
What disadvantage this mass spectrometry which you use?
I don't understand what I eliminate.
All analytical device has its disadvantage. I know, and this mass spectrometer which you use in your experiment have it is your disadvantage. I want to know how do you eliminate this disadvantage? It's interesting for me.
Cosa sono? Non ho capito la parola. Excuse me, I don't understand.
Because all analytic device... Yes, because there are, I know that there have spectral interferences which influence the result of analysis. But because all analytic people have...
okay, the situation of our experiment is quite simple.
No.
We analyze air if we want to make oxidation, and we compare the air before the oxidation and after the oxidation. We compare the spectrum we can get from the RGA. The same we can make with hydrogen or with deuterium or whatever it is, the gas we're using. So I have the spectra, and I can compare spectra, one and the other. That is...
okay, I understand. Thank you.
Okay.
Just...
Finished?
So thank you for all the speakers of today. The session is now over. We will restart tomorrow at 9 with Professor Carpinteri. Thank you.
Alberto.
What is your name? Dube.
Manuele, abbiamo finito o ce n'è un altro? Finish, thanks. Finito. Tomorrow at 9 o'clock? Yes, 9 o'clock, good. Dinner 7:30, yes.